So this is the two-way classification model we discussed in the last recording. So here the idea was that you have one observation in each cell and you have no interaction between them in some sense. So your model is yi is alpha I plus beta j plus epsilon ij. And we assume the same thing about epsilon ij's. They are like mean zero, variance uncorrelated, and each variance sigma squared. Okay. So I'll just try and devise a test for these. First thing is you do the residual sum of squares. That is R naught squared. So the first thing is for testing purposes, let's run testing. The first thing is that R naught squared that you do, right? So that's at the minimum. So that's going to be all the estimates subtracted from the total guy. So it's going to be I equal to 1 to capital I, sum from j equal to 1 to capital J. I have my observations yij, and I subtract the alpha I mean this is yi dot bar minus y dot j bar plus y dot bar whole square, right? That's what the estimate for this guy is. The mu plus alpha I was this, so I just put that guy in there. Okay. So if I have this minus this, the plus sign comes here, and then so now that's going to be, this one can show that this is just going to be equal, distributed as sigma squared times chi squared. I think it's I minus 1 times j minus 1. So the degree of freedom you can easily calculate how much is this, not hard to show. But this is not so illuminating, but what's illuminating is how to split the sum of squares, the above guy. So split them in three parts. So one is the sum from I equal to 1 to capital I. The sum is j equal to 1 to capital J, or yij minus the total mean, like before. Then you have, you subtract, once you do this, the last two you have taken care of. Then you have each of them, you have j times the sum from j equal to 1 to capital J. Sorry, I equal to 1 to capital I, sorry. I have the j and then the I. I have yi bar dot minus y dot bar whole squared. And then minus I times the sum from j equal to 1 to capital J of y dot j bar minus y dot bar squared. Can you size it a little bit? That's something, that's simple exercise to check that this is the same as this guy. So both these are same, and both these are distributed as like the same quantity, so it's the chi squared R. That's the distribution is R naught squared. Very nice. Very cool. Now, so now what do I want to test? So one hypothesis I want to test is there a difference in the treatment, right? So let's call this as H alpha naught, let's say. One hypothesis is the following, that they're all the same. That is alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to alpha sub j. Right? Alpha sub I, sorry, I treatments in this. So for this, I have to go and look at each of the alpha treatment blocks. So I'll call this alpha R1 alpha squared. Right? So that's going to be equal to, I will take the yij minus, I'll just always subtract the block out, so the mean block out. So I'll take the whole squared, and I'll sum from I equal to 1 to I, and I'll sum from j equal to 1 to j. Right? And this you can rewrite in a different way. So this you can rewrite, but the key thing is that R naught R1 alpha squared minus R naught squared, which is what you're interested in, that will just come out to be just if you just think a little bit simple as to check that this person just comes j times the sum from R equal to 1 to j, or sorry, j equal to I equal to 1 to I, sorry, I equal to 1 to capital I of the yi bar dot minus y dot bar squared. Something one can check, that is if you took R naught in this one, right? And if you want to test, this is the statistic that you'll use to check if the means are equal. If you want to test this, this is the treatment. So let's call this treatment. Make it in pink. So treatment is a treatment test. Right? And the other one is the block test. So you can do the block test. Let's call the block test in yellow, perhaps the H naught. Let's say is this one. Call it the beta one. So that's what that means. All the betas are same. We'll have beta one is equal to beta two is equal to beta three is equal to beta sub j. If you want to test this, then you have to go look at the beta squared. So let's look at the beta one. So it's going to be R1 beta squared. So what you do, you will take the yij's and remove off the mean from each of the I. So it's yi bar squared. Again, you will sum from I equal to 1 to I and sum from j equal to 1 to j. So same thing again, you subtract R1 beta squared minus R naught squared as before. And this is simple exercise. You can just check it's going to be just I times, I think I put a minus sign here, mistake, there's no minus sign here, just j times that. It's just I times, because the minus sign was there in the R naught squared right here, right? So it just be, if you look at it carefully, it's just going to be just I times the sum from j equal to 1 to j of y j dot j squared minus y dot whole squared. It's a simple exercise to try. I don't think it's very hard to do. Very good. These are two statistics you will use to test for the two appropriate means. Now we can do the ANOVA table. So here I will not do like previous time. I'll just state the result. So then after that you can go and compare. So let's write each column down. Let's come here. Let's say the first column is okay, this down. So make it white perhaps. Okay, yellows. Okay, let's do yellows time. The ANOVA table. So the first one you'll have the source, right? The sources. So what are the source going to be? The one source is going to be the treatments, right? That is so let me add this treatments. The first one, this is one you want alpha 1 equal to alpha 2 equal to alpha I, right? So make this a little smaller. Treatment part right here. So it'll have its own sum of squares. So, but let's come back to that in a second. The next one will be the blocks. Are they different? That is beta 1 is equal to beta 2 is equal to beta j. You want to test the blocks are different. In the block here, second row, and then here you'll have the cell. Each cell is different, right? So you have to do the cell. Let's say so you combine both. You combine H naught alpha and H naught beta. Combine both. So that's like the cell one. And then you'll have the last one is the error like we had before. That's the residual, right? That's again, let's just make it a little smaller. So like this one comes up here. And the last one is the total one. Let's put total. Everybody. That's what you'll have as the source, right? Then let's look at the sum of squares. Let's call that as SS, as sum of squares. So each of them will be independent, be each of these guys, right? So what will it be? So first guy will be like S alpha, S beta, SC, and SE. The last one, let's call the ST, right? So let's call the S alpha. What's the S alpha going to be? Let's write the first row. I'll make it smaller, so I'll move this across and I'll make it smaller and then bring it across, no problem. So let's write S alpha, the first guy. That guy is going to be what? This guy is going to be, sorry, in white or in white. So S alpha, let's call it as is going to be just J times what we had here, right? This exact statistic right here. This is y dot maths. So let's write that down. Let's copy that down, put that here. Yeah, then this is going to be S beta. That's going to be the same as the statistic we got for this testing this guy. So we can take this guy up right here. Let's copy this. Let's bring it down here. Let's game this one. Then what's the cell going to be? The cell is going to be S. Is this going to be add the two up, right? So SC is going to be just S alpha plus S beta. There's no problem, right? And the error one is the whole one, right? That's what we have. The SC is the whole one, right? SC is this R naught squared one, right? It's the one that's the error sum of squared that we have. Let's take this up. Let's copy this. Links down. That's the other one. And the total is everybody, right? The total is going to be just ST. Let's call it ST. This is going to be summation I equal to 1 to I, J equal to 1 to J. And you have just Yij minus Y. The whole square is what you have, right? These are the sums you'll have in this computation. So make it all smaller so that I have no space right there. Other columns. So make it all smaller. Let's make it really small. Quite cool. Go a little bit smaller as well. Very nice. Sorry, but that's not so small. Let's go. Yeah. Let's bring this guy down. Let's bring this guy. Let's bring this guy down. Let's bring this guy down a little bit. What's the bar going to be? J is going to J. It's going to change. Very cool. That's what you get here. Here all the bars have come out. So this is not the bar. Sorry. Undo. Just move all the bars down. Very good. So once you have this, then you just have the last one. Then after this, you have the degrees of freedom. For each of these guys is going to be the freedom. So first guy is just I minus 1, right? It's just easy to see, right? I minus 1. Second guy we know is J minus 1. This guy, a little bit careful, just add the two things up. So you get I plus J minus 2. This guy we know is just like the R before, it's I minus 1 times J minus 1. Okay. And the last one is just IJ minus 1. Okay, that's easy to see, right? That's the degrees of freedom, guys. And the last one is the mean squared. So you have to do the same thing. So the mean squared is just going to be S alpha by I minus 1, S beta by J minus 1. And this is just SC by I plus J minus 2. And this is going to be SE by I minus 1 into J minus 1. And the last one is ST by, last one, totally don't do anything. Utilize. Then you make it a little smaller so that the F statistics down. So to do the final testing, all you do is look at the F statistic that you have in mind. So the F statistic is what? You can just do several F statistics, one for the treatments and one for the blocks. So it's called mean squared. So then this is going to be the F statistic is going to be here, is going to be F alpha. For the alpha is going to be just S alpha by SC. So you do J minus 1 by I minus 1 times S alpha by SC, right? And similarly here you do F beta is the same as this guy. So same as J I minus 1 by J minus 1 times S beta by SC. These are the two F statistics that you keep in mind. And that will give you the entire answer. Actually, there's just no, sorry about this. There's no I minus 1 here. There's J minus 1 times I minus 1. That'll be the F statistic that you can work with and show that that's what the correct chi-square will be. The chi-square and correct F will be a ratio of these guys. So what we'll do is this is the ANOVA table. I'll just call the ANOVA table. So the ANOVA table. And what you'll do is you will just appropriately test this in the sense that if these F statistics were large, you just throw it away at the null hypothesis. If they're small, you keep the null hypothesis. So what we'll do is we'll come next time and we'll try to implement this via our code and show that these tables exist and what the tables mean and how to do the testing.